Okay. We're very happy to have Lev Rozansky to come visit and give us a talk on link homology from M theory.
Thank you for inviting me. So I'll try to illustrate how to use a certain technology in computing link homology and perhaps other invariants related to Donaldson-Thomas through the use of D2 branes. And I will use a very simple example to illustrate the technology. So you may feel that I'm telling you things that you know very well, in part from Mina, and that I'm trying to hide this fact by using fancy language. And you will be correct in part, but there are more complicated examples of this technology where it's harder to get the right answer without using it. Let me remind you the standard construction of link homology. So you begin with a link in a free manifold, and you want to categorify Witten-Rashtick and Turayev invariants corresponding to a supergroup. You have two types of defining representations, CMN, where M is even, N is odd, and CNM, where they're reversed. And Vafa and Guri suggest that there is a way to produce them from M theory, not only these representations, but also their symmetric powers. So to each link component, you assign one of these symmetric powers. I call link K because L is reserved for Lagrangian submanifolds. There are two standard situations where one is when you study Chern-Simons-Witten theory, you use the group UN presented as UN0, and you use the even representation. Therefore, the invariant of the unknot is quantum N. So let me put it here. So unknot is just quantum N. But then if you categorify, most categorification constructions beginning with Kavanagh, if you're honest about them, they use the same, for example, UN0, but the odd representation instead of the even one. And there are two consequences. First, instead of symmetric powers, you see skew-symmetric powers because you're symmetrizing the odd one. So you get minus. OMG. OMG. Sorry. And the second consequence is that the invariant is negative Q. This explains, by the way, the negative sign in Kaufman bracket. If you go back in time to the way Kaufman defined Jones polynomial, it was very natural for him to assign negative Q minus Q inverse to the unknot. And Kaufman bracket is the first hint that the theory can be categorified. And Misha Kavanagh put a lot of effort in trying to get rid of that negative sign. But the natural sign for him is negative. So it's normal.
Sure. What is a Q bracket then?
Sorry?
What is a Q bracket then?
Q.
This is a Q.
Oh, sorry. It was quite some time since I wrote it. I'm sorry. Of course, thank you. It's quantum N. And in this case, it's negative quantum N. So most of categorification constructions, the ones that yield finite dimensional homology of, say, of an unknot, are of the type when the representation is odd rather than even. And that's why when you decategorify, they naturally give you negative.
I guess my question was more naive. What's the definition for that symbol?
Ah, that's okay. That's sorry. That's q to the n minus q to the negative n divided by q minus q inverse. So it's the sum of powers of q. Okay, so the M theory setup is you consider 11-dimensional manifold, which is cotangent bundle to your 3-manifold. This gives you 6. Then you take a hyperkähler manifold of complex dimension 2. In this case, Taub-Knot. Just a moment. Taub-Knot is simply C2 with a funny metric. So this C2 you can present as a product of two C's. Let's call it C with coordinate X and C with coordinate Y. And geometrically, they have the shape of cigars. But for our calculations, you may just think that this is C2. And 11th coordinate, say real line, I call it cobordism time. To produce Chern-Simons of U and M, you need n plus m, M5 branes. So for those who do not like branes, a brane is what physicists used to call ether. That's a material object that vibrates and moves, and its vibrations create electromagnetic fields. Sorry? Okay, so you have n plus m such things. You place them on 0 section of M3 and either on CX cigar or CY cigar. So you distribute, and that distribution tells you what superalgebra you will get. And they run along cobordism time. So everything, in fact, runs along cobordism time. And then to every link component, you associate a conormal bundle in T star M. So it's a Lagrangian submanifold. Again, you place it either on X cigar or on Y cigar. And this will give you, so if both are placed on the same cigar, Chern-Simons and the knot, then you get the even representation. And if you place it on the opposite cigar, then you get the odd version. So assuming that this thing is small, in quotes, you get a 5-dimensional theory on Taub-Knot cross cobordism time. And the question is how to count the states of BPS particles in that theory, whatever this means. So BPS particles, you may, again, if you're not a physicist, think of them as particles like electrons. Some may fly around the 4-dimensional space, which is Taub-Knot, but we're interested to the ones that are attached to either of the cigars. So you may say that these are quantizations of the vibrations of these cigars, because cigars are material objects, since they support the M5s. Taub-Knot has a symmetry, 2 C stars.
Can you explain what it is?
This is the funny metric. So it is important for future that it's not the flat metric of R4, but a funny metric in which, if you look at a big sphere in R4, it's 3 sphere, which can be presented as a bundle of S1 over S2. And as the radius extends, both the radius of S2 grows and the radius of S1 grows. But in this case, the radius of S1 has an asymptotic limit.
You want some kind of special metric of G-star?
So Sergei Cherkis told me with any uncertainty that if you take a quotient by the action of U1 for the purpose of duality, you should make sure that the orbits of that U1 are of limited size, preferably very small. So for some constructions, one would like to take a quotient by the action of this U1, which rotates them. And so you want the orbits to have finite length. So to be safe, assume that this is Taub-Knot.
No,
Cherkis assured me that near the zero section, you can endow it with the Calabi-Yau structure. And you can definitely do it for S3. The answer is no. Okay, so here you have two C-star actions, and the states of these BPS particles have weights with respect. So you want to count them together with the weights. And this space of BPS states is what's link homology. And if you take its graded Euler characteristic, then it's equal to Wittgenstein-Turaev invariant. I'm cheating a little bit, but just a little.
So can you scroll up a little bit with that here? Okay. So far, what I understood is like you have 11, which is like 10 plus 1, the 10 is like collision bundle or something or something like that.
Yes.
And you have some 5D that won't be cross some R time.
Oh, sorry.
And then what is the?
So the topology, the three-dimensional topology is hidden. All you see is this 5-dimensional quantum field theory with supersymmetry, and you count particles of special type, and that's what link homology is.
Okay.
So because of string dualities, there are tons of different ways of counting this. So lots and lots of ways. And our technology is, first of all, we consider these particles as M2 branes, so objects of space-time dimension 3. So we consider them as material particles as opposed to quantization of vibrations. This is very well known. So a particular M2 brane has the following shape. It's a surface inside the Calabi-Yau with boundary which lies on M5s. It is a point in the Taub-Knot space, and it extends along cobordism time. Now, we want to put the branes, the M5 branes, in such a way, or we hope that these surfaces corresponding to individual M2 branes will form a tight stack. So I'll just call it sigma. So they will all lie like pancakes or even thinner. And that stack of pancakes will be crossed by M5. So I will consider a simple particular example later. So if you do not see how this works, don't worry. Oh, it's intuitive. I don't know how to work with mathematical stacks. So I mean a stack of pancakes, but very, very thin. Yeah, sorry, I should have said that. Now you find so here we start to deviate a little bit from standard approach.
So what would be like crossed by M5s?
So you will see an example, because some you have many pancakes in a stack. This stack is intersected by M5 branes, and some pancakes end, and some go through. So the number of pancakes on different sides of M5 will be different, generally speaking. Again, I will give you a very special, clear example. So
sigma is like homomorphic distance.
it may be, in our example, it will be strip. It will be segment cross R, as you will see. So we want to compute anything reliably, we have to turn it into string theory. The way to go to string theory from M theory is to find a U1 symmetry of 11-dimensional manifold. It doesn't have to respect branes in any way, and take the quotient by its action. So you lose 1 dimension and you get string theory 2A. So now the question is, what's the choice of U1? There are two popular choices. Choice number 1, take cobordism time, wrap it into a circle, and rotate the circle. Choice number 2, rotate Taub-Knot by C sub q. A less popular choice is to find a U1 symmetry of M3, of your free manifold, and take a quotient by it. And this is what we do. So then M5 branes, the way this will work is Chern-Simons M5 branes turn into D4 branes. They lose one dimension as you take the quotient. The link ones do not lose dimension and they become NS5 branes. M2s are placed in such a way that they do not lose dimension, and therefore they become D2 branes. A stack of D2 pancakes, its movements and vibrations are described by three-dimensional, because these are three-dimensional objects in space-time. So three-dimensional theory with supersymmetry n equal to 4 and with matter. So I'll explain later what this means. And if this manifold has stable points with respect to U1 action, they will yield D6 branes. So they may appear in 1 hour. So the example that I will consider will have no D6s, and that's why it will be so simple that you will say that I'm trying to impress you by telling you standard things in fancy language.
You want this, your link to be branes on the D1?
No, no. In fact, it will be transfers.
Okay.
And again, you will see a very specific, simple picture a little bit later. So then, what we have to do is compute the states of these D2 branes are the particles. So in order to find the states of the particles, we can find them as states of the stack of D2 branes. So instead of studying five-dimensional theory and see how the defects vibrate, how the cigars vibrate, instead we look at the inner physics of D2 branes and find their states. And this is emphasized, by the way, in the paper by Frenkel, Aganagich, Frenkel, A.Oblomkov. In the part that was written by Mina, it's emphasized that both give you the same answer. So we will be looking at the states of this theory, and this will be the link homology. And why do we use this approach? Because describing these states can be done with the help of our paper with Kapustin and Saulina, where we studied such theories with the topological twist. So the main example, now everything should become very...
The twist that you used in the paper with Saulina was a twist that preserved, so the Riemann theory has SU2 times SU2R symmetry. It preserved an SU2 symmetry. It made use of an entire system.
Yes. Yes.
In
So
our
I
work
will
with
tell
Andre-
you what we twist. I'll tell you.
In our work with Andre, there's no such.
So it's good, which means that, well, either what I say is wrong or it will be somewhat new to you. In fact, okay, so this picture, as I said, is a bit different from what you did with Andre and Edek. And we will argue whether. So here's what I want to do. Inspired by Mina, I want to take M3 as a cylinder. So geometrically, it's a cylinder, it's C star. Cross R, I call it break time. And this is the picture that you see in every Mina's talk. It's a very inspiring picture. It's a very inspiring picture. And in fact, so T star M3 splits into two pieces, T star C star, which is very good because it invokes, for example, old paper by Witten about M theory and brain and gauge dynamics. And we'll use it towards the end. So T star of this is C star cross C. T star of braid time is braid time and let me call it dual braid time, just cotangent direction. Here is the Taub-Nut and here is the cobordism time. Now the branes, the Chern-Simons M5s wrap the cylinder and they're at the center of this C. They go along the braid time and originally they would all sit here at the origin, the zero section. But we spread them, we push them off in the direction of dual braid time. In this setup, it's very easy to push M5s of the zeroth section, which is good. Then they go, let's say, along the Y cylinder, the Y cigar, and they go along the cobordism time. The Chern-Simons M5s are cotangent spaces at the braid points. They are, again, lines going along the braid time, but I push them off even farther in the dual braid direction. They wrap the X cigar to reproduce standard categorification constructions and go along cobordism time. Now you can see the particles.
Can you repeat? I understand. Okay, too fast. So I understand M3 is that cylinder cross R, and then you decompose the T star M3 as T star.
Yes, T star C star and T star are. Sorry, let me. Yes.
And then what happens?
And then you can see the M2 branes, the BPS particles that we have to count.
Okay.
So in Taubnut, they're just particles living near the intersection of the cigars. They go along the cobordism time. And the most interesting part is in the cotangent space to the braid time. So you see this strip, they're stretched. These pancakes are stretched. One side of those pancakes ends on Chern-Simons M5s, and the other end on braid M5s. So if in these pink numbers are the thickness. So here I gave you a picture. If you look transversely to that stack of
so that shaded region, is that the image of the?
These are M2s, yes.
That's the projection image of the.
So M2 is a three-dimensional object in that M11. So it sits at, these points are supposed to be very close to each other, by the way. The braid is supposed to be very tight. So they sit here, somewhere in between them. They sit at the center of C. They form a strip here, and they sit near the origin of the Taubnut, and they go along the time slide.
So the M2 projects to T star C cylinder.
Yes, yes, mostly a point. They vibrate somewhere in between these. So if you look transversely to this pancake stack, and again, I'll give you a bit more detailed picture. You will see how this works. So if you look transversely, you see that in the middle, the thickness is 4, but then 2 pancakes ended on this D4. So you're left with 2 pancakes that ended on this one, and so on. Okay. Again, it's not a standard name, so it's culinary taste. So now we take the quotient by U1 that rotates the cylinder. Now, regarding what Mina's comment, I strongly suspect, and we can argue, that Mina uses, instead of taking C star, she takes here a torus.
No.
So let me put here big question mark.
And why do you use the numbers 2, 4, 3?
Just for illustration.
Because for particular, not theory purposes, you need to pick one, depending on which not variance you want.
So here, if I wanted to construct a link homology, both black ones would have, so this is the U2 case. So they would have, so I want 0 weight, so they must be equal to each other. Again, this is just to explain how this is placed. Okay, so we take the quotient by the action of U1 that rotates the cylinder, and we end up with 2A theory, which is exactly what we had, except that the cylinder becomes a line. So this stack carries this supersymmetric Young-Mills with matter. So it has its vibrations, this is the ether. Vibrations include Young-Mills fields. They can move along C and along the cylinder from the center, but those movements are twisted. So the twisted directions are C and R cylinder, which means that the positions of pink points in here become connections rather than scalar fields, and their positions inside the Taubnot are not twisted. So if you have one particle, it will be described by two complex fields telling you where it is in this C2. And if you have a stack of n, it is described by two matrices whose eigenvalues tell you the individual positions. That's the rough idea. So that's what physicists, string theorists will tell you. So you get two matrices. So the matter, the extra matter is T star GLN. GLN X and GLN Y, telling you where the particles are on, how they project on both cigars.
Sorry, I'm confused. I thought your Chern-Simons brain zero section, and your not conormal is like leading in the conormal direction. So why in the picture you put up there, your Chern-Simons, no, just go up to see the T star R brain.
Yes.
R brain, yeah.
So since
Shouldn't they be like transfer something in this?
no, because they are the braid itself is the line R bur. So conormal is just the zero section, same thing. The conormal to the zero section is the zero section. If you have a cotangent bundle, what would be conormal to its zero section? It will be the zero section. It's in the cotangent direction. You can go in the directions that annihilate the tangent ones. So you cannot go anywhere in the cotangent.
Okay, okay.
So conormal to zero section is the zero section itself. That's the answer. Okay. So the Higgs branch of this theory is what mathematicians call commuting variety. That's this, you can say it's Nakajima quiver of this shape.
Sorry, but when you talk about the system of brain, you don't have to say anything else. I mean, you already fix the Lorentz fix. You don't have to do anything more.
Yeah, and I don't do anything more.
But the Higgs branch of this theory will depend on the numbers.
Yes. So I'm talking about local stack.
Got it.
So locally, in the pink area, that's what it is. So how does the braiding look in this story? So just a few pictures to make it more transparent.
Can I ask you a
Yes.
question for slowing down? So can you scroll up just a little bit? Okay, there's the ND2 carries. So this ND2 comes from the NM2. That's like the
Yes.
and then what does it mean? Or you just okay? You just say I just want to have this meta representation T star GL.
No. Since I know how they're placed, I know how to describe their movements by quantum field theory. So same as electromagnetic fields, light is vibrations of ether. So here we have the same thing. This is ether, and its vibrations are described by this theory.
But why is the GLN not secret?
So GLN comes from the following fact. These ethers or branes are points in Taubnot. So each one, suppose I have just one, instead of 2, 4, 3, I have one in between. It would be a point here. So to describe its position, you would need two complex numbers.
Yeah,
Which means you have two complex valued fields here. You map this into Taubnot.
Okay.
Two complex valued fields. But if you have, let's say, 4 of them stuck together, then their positions are not described by 4 Y fields and 4 X fields, Rather, they're described by two matrices, 4x4 matrix for y and 4x4 matrix for x. And the positions are eigenvalues. So this is very similar to how you define, say, Hilbert scheme of points on C2. You have two matrices and the actual positions are. And this comes from string. Again, I don't want to go into. That's because you have strings which endpoints are attached to individual pancakes. And so instead of having, and each string is an entry of a matrix. So that's why you get n squared. So, but again, it's. So, yes.
So what will quotient by U1 play in the story? Do we need the quotient by U1 to turn it into a nice supersymmetric theory?
Yes, because the vibrations of D2 are much simpler than vibrations of M2.
So what
It's
does it look like before we quotient out? I guess, when you-
I don't know. People say, I've been told, but I don't know. So people say that they can describe the movements of M2s. But again, I don't know. But the movements of D2s are described by the theory whose twisted version I understand relatively well to be able to calculate things. So if you look at, so how do we see the braiding? If this is the cylinder that is turned into a plane minus the origin. I just splashed it or exponentiated. So this is the cylinder, and this is the dual braid direction. That's the direction along which they're stretched. And I reversed the picture a little bit. So the braid M5s now are on the left. In that picture, they were on the right, but now place them on the left. So you see that M2 branes go like this. So if this point projects to the same, if these two project to the same point, then there would be a special thing that a piece of pink M2 will be between these two sand points. So they have to stay away from each other in the projection. Now, it is important for some purposes to maintain the order of their projections on the braid, on the dual braid direction, to keep it the same as their radial order on the cylinder. You have to maintain them the same for the uniformity of stability conditions for the quiver that will emerge. So here, just trust my word. You want to.
Yeah, so the M2s are like two-dimensional in this vector, in this six-dimensional thing, right? M2.
Yes.
And your project, you can somehow.
Now I draw only three dimensions: the cylinder and the dual braid time.
But the braid is running along the braid.
Yes, so I froze braid time, so it's a snapshot. There is no braid here.
Okay.
I fix braid time, it's a snapshot. I'm looking at the dual braid direction and the cylinder on which the points move. And this is what I see.
Oh, okay, so your M2 is actually purely living inside the T star of R braid, and you are throwing with the forwarding direction of R.
Yes. So I throw away the braiding direction, and so I keep this one and the cylinder, and I flatten the cylinder to make it easy.
Sure.
So this is
segment.
so it's C. So M2s go and then they will end on D4s somewhere to the right. I'm concentrating on the braid ones because they will give me the braiding. So the actual braid is these crosses. So when you talk about topology, you watch how these crosses move in the vertical plane.
Like the braid is how many dimensions? Like in the
So the braid comes from moving points on the cylinder. So these are the points, and this is the cylinder that is flattened, exponentiated. So it's C minus the origin. And so so this is a movie, this is a frame of a movie. As you turn on braid time, these points will start to move, the crosses. And I do not want the crosses to collide because then the pink segment will be stretched between these two. And that will change the physics. The Coulomb branch will emerge. So we don't want that. So for some technical purposes, one would definitely prefer to maintain the order in which they project on this line to be the same as their order in the radial direction of the cylinder. So therefore, when they take a braiding here, you will see that they intersect here as well, because we want to maintain this order. So what we will see in a few minutes will be a fake braid. We will be looking at dual braid time. So we will not see the actual braiding. It may look like they're intersecting, but the actual braiding happens elsewhere. So now again, I flipped now the cylinder goes this way. That's what remains of it, and after the U1 reduction. And this is the dual braid time. And this is the picture now in the presence of D4 branes. So this is what's very familiar to Mina, and I'm sure she talked about it many times. So you have now the strip you will see when you look this side.
Well, the D4 is like the CS.
So yes, so D4s give you the Chern-Simons theory. These are the source of the knot or of the braid, and the actual braid in the D4 space is produced by M2s that are stretched, and this is the standard Mina's picture.
So why do you have M2 between the CS and CS?
Because roughly speaking, some of them can end here and some of them can go down. So this is the thickness of the stack of pancakes. Here the thickness is 3, here the thickness is 2. Remember how we had the strip and it was 4 and 2. So I could have here 4 and only 2 left there. But they can move freely back and forth. This is what creates the dynamics. These pieces can move here back and forth. They don't have to be strictly below.
So all the actual really are between the braid brane and the CS.
So they're stretched between braid and Chern-Simons, and this is but some pieces here can move back and forth. So this is elementary mechanics of braids. So when braiding happens, what we see in the strip is that these two lines cross when they braid in the transverse cylinder, because we want to keep the order of them here the same as the radial order on the cylinder. So that's the picture that we'll see. Okay, in order to reproduce cups and caps, you know what, maybe I'll skip this one just because
So far, we've learned which theory one should study.
sorry?
So far, one has learned which theory one should study.
Yes,
somehow
yes.
follows.
So yes, so let me.
So the answer that you'll get a quiver gauge theory and you'll study braiding of
Yes, yes.
this language. F5 parameters and the category of B branes should somehow encode linking variants.
So we're yes. So in topology, in addition to braid, you have caps and cups. And the nature of caps and cups is a little bit involved. The actual cap that happens here is that you have a wait a minute. You have just a moment. Certain picture somehow disappeared. So what happens in topology is that two lines going up meet here, and the number of boxes in the Young diagram gets redistributed. So this is what happens because the number of NS5 doesn't change. NS5 brane doesn't go back. They all go up. But what happens along the braid time? But what happens is that the number of pancakes ending on individual ones is changing. A small strip of pancake tears off and goes elsewhere. I think that's what goes on.
You shouldn't think of it like that. You discovered which theory you should study. And the caps and cups are boundary conditions, that theory. You can think of it as some kind of the main model, the trivial.
Yes, they're interface. So I think what, yeah.
An actual boundary, that's all that you use.
Yes, so I just want to say that my strong feeling is that a piece of one of the pancakes here tears off and goes elsewhere in transverse directions. And this corresponds to the idea that these were distributions, category phi, E and F, when you categorify Lie algebras. So this is a gluon. This piece looks like a gluon that is torn off. But again, I don't want to go into strings. So where do we want to go with this? So we want to construct the space of states of this strip, because the space of states of the strip is the space for the three-dimensional theory of D2 branes. So the space of the states of that strip will be the link homology. And how do we want to construct it? With the help of the two category. So the goal is to understand pictures like this one, for example. So this is a piece of the strip in the braid and dual braid directions. And here a braiding happens. So there is a category associated to this dashed line when you cut through. There is the same category on top. And there is a category of this dashed line. So this semi-disk with the braiding inside creates an object here. And this object creates a functor from this category to this category. So again,
Sorry, can we just go up? Which theory are we studying? Let's repeat that.
so we want to study the theory on the strip. And some
So,
braidings happen.
question, the length of the strip, does it matter?
In fact, you can say that it's infinite, but because of cups and caps, eventually these pancakes will be in such numbers that they will be fixed.
No, the length, that length, it's completely irrelevant.
It's topological, yes.
0 or 17 or anything. That's not
At least non-zero, but it's topological.
It doesn't matter.
Yes, yes.
So why do you get a 3D being on?
Because instead of squeezing, I could squeeze them. I could squeeze these and these. And so I will lose one direction and I will get a two-dimensional theory.
So we just look at the two-dimensional being on?
Yes, but then you will lose the fact that the actual braiding happens on this side. It doesn't know anything about this. So the braiding is universal, does not depend on how many D4s you put.
No, the theory which Informal is studying remembers exactly where you are, it remembers the braid. Because that.
Yes, so I want to keep it finite. We're talking about this link.
Yeah.
I'm sorry, I thought you were talking about this one.
That's like.
Yes, so you can squeeze it to 0, and that's what you do in your paper. But you can also keep it finite. And for example, you can, to make it simple, squeeze the sand ones and squeeze the black ones. So the braiding happens on this side and does not depend on what happens here. So there is a universal braiding that describes, and let me now go back to this picture, go forward to this picture. So the braiding happens here.
Sure, the same way all braids are n-strand in which they just have n-strand.
Yes, so it's a physics of D2s ending on NS5s. And then you put something on this side, and this gives you a particular implementation of link homology, or more generally, depending on what your M3 is, it doesn't have to be.
But we can simply, 3D being models are more valuable two-dimensional.
Yes, but so the reason why I use them is, one is that it helps me to explain what happens in superalgebra case in the language here. And number two, you separate the braid from the actual gauge theory, Chern-Simons gauge theory. Chern-Simons happens here, but this side doesn't know about the braiding. The braiding happens here. So eventually, a little bit down the road, if you don't kick me out, I'll explain, for example, what to place here so that you would get Kautas Kamenetzer, for example. So I'll just tell you how to.
And you don't know that? Sorry, what do you mean? So you get Kautas Kamenetzer? Which?
Oh, sorry. Yes. So this gives you Rina-Anno implementation. The theory that you get from here gives you Rina-Anno affine tangles and so on.
I mean, Kautas and Kamenetzer studies.
Kautas and Kamenetzer have a very particular variety. Yes. So the question. Not quite. They're not hyperkähler.
Yes, because they included some that you can.
Okay, you will see. You will see. So you will see. I'll show. Maybe it's no. We'll see.
Being hyperkähler is important. Make the life more difficult that it's not. Well, rather you lose some information by the fact that the original figures are not hyperkähler, but they're very close to what you actually want.
Yes. So the question is how to describe the categories of these dashed lines, and that's what I will sketch.
So you associate category to the line or to the region?
So in the standard theory is that if you have an n-dimensional topological theory to an n-1 dimensional boundary or cut, you would associate a vector space of states. And if you cut that one, so to n-2 dimensional, you would associate a category, and then you would associate a two category and so on. So this is what goes on here.
Theory. Your three-dimensional theory is really all relevant part of that two-dimensional, right? So I could simply study the category of bounding conditions, and that's really.
Yes. So in two-dimensional theory, this would just be a point. So it would be a category. Yes. And so here it's also a category, of course. And same as here and here. So we want to assemble them through elementary pieces. They intersect these interfaces, the Chern-Simons and the link ones and the braid ones. So each of these is an interface and they intersect. So the question is how to construct this category out of elementary pieces. So now we turn on symplectic geometry in the context of algebraic geometry. So this is symplectic algebraic geometry. So we want to construct this and this categories out of elementary pieces.
The one category or two categories?
The one category. But in order to construct it, we have to cut the dashed line. We have to cut it here and here and here and so on. So to each red cross here. Yes. Yes. So each interface gives you a functor. These give you boundary objects. So you take an object, apply functor, and take hum with the last object. And that's what I want to explain how this works.
So the red line is also the category.
Yes, but it is assembled out of in a two category way.
So the reason you draw this 2D and you say you are doing 3D is because you killed one circle.
So I take a slice at fixed braid time. I take a slice at fixed cobordism time. The time of this 3D theory goes along cobordisms of braids. So I fix that time, the 11th time in the original picture.
Okay, good.
And so two-dimensional theory now becomes a strip. A strip is two-dimensional. It's the space of the D2 theory.
But you could have also just told us at this point, okay, here is a category of coherent sheaves on some space, and I'll tell you how to build it out of pieces.
Yes. So
Okay,
this will turn out to be category of coherent sheaves over Nakajima quiver variety. And I'll build it out of these pieces again, I'm telling you something that you know in a fancy way. Why am I doing this? Because it can be generalized to other cases when, for example, instead of Taubnut, you can have a two-centered Taubnut, or you could, I mean, there are many interesting questions, or you could replace Mina's cylinder with a
studying a category of B-branes on some homomorphic symplectic manifold, and you're telling us how to build it out of pieces. In which generality will that work? Build it out of pieces associated with like that.
So for example, you could replace Taubnut with multi-Taubnut, multi-centered.
No, in the world of coherent sheaves and a symplectic manifold, there's no Taubnut.
There is, okay, look.
Okay, just stop. Yeah.
So generally, if you have a symplectic manifold, which is a cotangent bundle, so this supports a 3D theory, and this is a spatial slice. A boundary condition is a pair of an algebraic variety and a function on X cross Z. I'm assuming that X is affine to make it simpler. And a home between two such boundary conditions. Something. Yes. No. Completely from outside. Something that you bring in. Something that lives on the boundary. X lives in the bulk. T star X lives in the bulk, and Z lives on the boundary, and you get a superpotential. And so a home between these two boundary conditions, that would be a line on the boundary, and we see a point because we fix time, is matrix factorization. So now come matrix factorization.
I want to say that a kind of boundary condition in whole theory is abstractly comes from 2D and 2 theory.
Which live on the boundary, interacting with the bulk.
Okay, and in fact, I could have changed my original word reading for just two-dimensional theory.
So two-dimensional theory.
We only need a two-dimensional theory.
We will
of ordinary B-branes in a two-dimensional sigma model.
Sorry, this is a three-dimensional one. So if it were two-dimensional, you would have here a sheaf, coherent sheaf. But
yes,
since it's three-dimensional, it's something else.
But I could have gone so, right, let's try again. We're studying a category of boundary conditions, which in a theory
Two
would have been
category.
two-dimensional. A two-dimensional sigma model with a B-type boundary, category of B-type range, coherent sheaf.
Yes.
All right.
Now this is a
you tell that thinking of this theory as having one extra dimension, you can describe that category of coherent sheaves of a two-dimensional theory in a different way.
yes, it will be
All right, so we'll see.
it will be the category, for example, the category of lines on the boundary. A line looks like a point because I took time slice. So the mathematical answer is that home between two such boundary conditions is category of matrix factorizations on this big thing. So that's the mathematical side. And what does it mean? If Z, for example, is a point, to make it simple, then W, the function on X, can be turned into the graph of its differential, which is a Lagrangian subvariety in the cotangent bundle of X. So in other words, you say that momentum is the derivative with respect to X. That's what this statement means. And then home between two functions on X, which is matrix factorizations, is approximately the same. It's not the same, but close to coherent sheaves over the critical locus of the superpotential.
But what I know I should study is exactly coherent sheaves on a homomorphic symplectic manifold.
No. Naive. So a boundary condition, naively, is a Lagrangian subvariety of T star X. a home between two Lagrangian subvarieties naively is coherent sheaves over their intersection.
The thing we actually need is a one category, the familiar one category.
Yes.
The categorical coherence
Yes.
for more complex.
Yes.
Fine. Great.
So it will come naively as coherent sheaves over the intersection of two Lagrangian subvarieties in a certain symplectic variety. But
So, and so in the original picture up there, you had like, there were a whole bunch of defects in the line.
yes,
So,
so I begin with the boundary. So the boundary is this.
can you explain still how to relate this picture to the original one, just to make sure that I understand what you're doing?
Yes, I begin at over here.
Yeah,
So
Great.
first I want to explain what is the last send line.
the last time line. Okay.
And then I will explain what is the interface and
Okay.
explain particular Z's and W's. So the critical locus of the difference between superpotentials is the bijective projection of the intersection of Lagrangians in the cotangent bundle, because each Lagrangian is partial derivative. So they intersect where partial derivatives equal to each other, where the differentials equal. So it's one-to-one in the simple cases. So if you say y equals dw dx, then for two w's, y's are equal where at the critical points of w1 minus w2. This is what I said here.
So this is D, or just describing more general like
Yes, so it's in classical mechanics books, it's action depending on extra parameters. You will see in a moment what it means. So if for an interface, you associate a similar thing. So suppose you have two cotangent bundles. So you put an extra variety and a function on the product of all three. Sounds a little bit intimidating. So it defines, this data defines the Lagrangian correspondence in the product of these cotangent spaces. So an interface is Lagrangian correspondence, again described in terms of these actions. So if you have a boundary condition and then a correspondence, so you squeeze them, you get a single boundary condition. Very, very simple. You have to take the product, so the extra variety will be Z1, Z12, the X1 that lived in between, and the sum of superpotentials. So from the mathematical perspective, it's rather straightforward.
So,
I mean, can you explicitly describe these operations?
I'll give you an example.
so do you think the function and the generating function is W and D, they are fundamental, or the Lagrangian itself is fundamental?
So the question is how to describe Lagrangian subvarieties in algebraic geometry. So for example, there are lots of singular ones. Famous in Hilbert's space, in Hilbert's scheme of points on C2, there is a famous Lagrangian subvariety where matrix Y is nilpotent. And it's singular, it consists of smooth pieces, but you have to take it together. So the way to deal with this, it seems the proper way from the algebraic geometry point of view, is to present your variety as cotangent bundle and describe the Lagrangian with the help of Z and W.
Okay.
And you will see this famous one described this way in a moment.
Just worried whether there's maybe equivalent description, like different D, different W describe the same thing.
Yes, yes, it's quite possible. It's quite possible that the same object is described in two different ways. Yes. So what is an NS5 interface between two cotangent bundles? Just let's forget about equivariance for a moment. So this is what you do. You have the pink quivers that describe these, and you keep only one arrow because we need the base. We ignore the fibers. And now Z is arrows going in both ways. So it's your standard. So here you have a combination of two Nakajima quivers. One is the pink ones, and the other quiver, you see only one edge of it. So it emerges as the Z variety, as the extra Z variety, these two Nakajima arrows. So we're slowly building the sand quiver, but instead of saying Hamiltonian reduction at the nodes, as Nakajima would say, we're doing this composition of interfaces in the other symplectic variety. So there are two symplectic structures here, unrelated. One is related to the pink one, and the other coming from the sand one. And these are two independent symplectic structures here, because we're talking about two intersecting Hanani-Witten type sets of branes. Anyway, the superpotential is going this way, index 2 trace, and going this way, x1 trace. Easy to guess.
Sorry, bring up again. I'm really confused about the meaning of these pictures. So far I understand, okay, you have this orange line for things representing the braid.
So yeah, so the sand one, let's call it yellow to make it simple. So the yellow line is related to the braid. And so yellow line separates two stacks of M2s. So you have two different theories of the same nature on both sides. The number of pancakes is different, N1 and N2.
Okay. Yes.
So this interface is described as Lagrangian correspondence in terms of generating function. So I add an extra variety, which is these homes times these homes, same as Nakajima would for a linear quiver. T star home from CN1 to CN2.
Sorry, can I explain what is phi 1, 2, and phi 1?
Sorry?
What is phi 1, 2, and phi 1?
Homes. So I should say, well, okay, sorry, I should have said that at the beginning. So Z12 in this case is T star home CN1, CN2. Describing this interface. CN2, oh, sorry, thank you. Sorry? Yes, yes. So something you would put as a Nakajima edge. So the pink quiver from the Nakajima point of view is a single small circle. So inside a small circle of Nakajima sits a commuting variety in this picture. So Nakajima would have I use different colors, this, and this. But inside that small circle sits a commuting variety secretly. This quiver. So Nakajima, just let me show you how they compose, and I'll make next statement. So
the W defines some Lagrangian.
yes, so W defines the Lagrangian subvariety as in classical mechanics, generating function.
And then what they're going to do with
So for example, if you have T star X and two Lagrangian subvarieties, so the boundary condition is Lagrangian subvariety. And what would be home between them? Naively, you would think that a home, which is a line on the boundary. You see, this is three-dimensional. There is an extra dimension going this way, time, and you take space slice. So this point is a line separating two boundary. Yes, similar to Fukaya. Except this is one dimension up, and it happens in algebraic geometry. Yes, so you have a defect line on the boundary. And what would you put on it? Naively, you would put a coherent sheaf on the intersection of these two Lagrangian subvarieties. But this turns out to be naive only. The right answer is you put a matrix factorization of the difference of W's. So from algebraic geometry point of view, the purpose of describing this is the proper way of this, or a good way of describing Lagrangian subvariety. Then you know what the home is precisely. This is the full answer. This category of matrix factorizations.
So this would be a specified boundary condition. So whatever theory you have solved.
So you have a three-dimensional theory, you have a two-dimensional boundary. On the boundary you have lines separating different boundary conditions. So each boundary condition is a Lagrangian. On the lines you have matrix factorizations of the differences of their W's and so on. And if they cross, and if sorry, so and you can have a point on the line separating two different matrix factorizations. So that would be home between two matrix factorizations, and so on and so forth. Will be a little bit more complicated, but I can certainly describe what happens when lines meet.
So there is a natural thing that you're saying.
Yes, yes, yes. So you know what would, so if three lines intersect on the boundary, then you know what category to assign to this and so on.
There are certain categories who these lines are singular.
So you have a defect on the boundary, an interface on the boundary, and it's colored by matrix factorizations, and then you can have a point on the line, and that would be home between two matrix factorizations.
Can I harass you?
Yes, yes, of course.
So it's possible to describe the classical theory with these Lagrangian boundary conditions, just in terms of visual fields.
Yes, of course, that's what we did with Kapustin and Solina. So it comes from physics.
Okay. So there you have Lagrangians.
Yes, yes, and we have a second paper with Kapustin in which we go into more mathematical precision. So yes.
So this is, in a way, this is what you described now, the gradients of local classical theory.
Yes, so it's a quantization of
There
a,
is no one.
so it's a quantum field theory.
All possible things to put on the boundary directly in the ball. Just like that. It doesn't fit with Lagrangian. Yeah. Something in the ball, and you put all possible things directly.
Kolya, when you put a representation on your Wilson line, it's similar, except that now lines live on the boundary, and instead of representations of the group, you put matrix factorizations.
This is still classical.
No, it's quantum field theory. It's a, what about Chern-Simons? Is it classical or quantum?
Well, when you set boundary conditions for connection between some Lagrangian separation,
Yes,
the boundary, that's still classical.
yes,
You geometrically quantize it, that's quantum.
yes, yes. So this is the story about quantization.
So far, we have classical. When you start to quantize,
Yes,
you will do some geometric quantization, will you have Lagrangian vibrations? Will you have these ingredients of geometric quantization or
let us discuss this separately. So I'll be happy to, because it will. So here you see that Nakajima quiver emerges, the yellow one emerges through the interfaces between pink quivers. Again, I'm telling you something very simple. Why do I go in?
Yeah, by hand.
Sorry?
Just look at put it. Right? It's not like it's emerged. It's consider the interface given by like a different quiver. You say like a different quiver.
Yes, yes, but Mina will tell you that this is how an NS5 interface intersecting a stack of D2s should look like. These are strings between pancakes on the left and pancakes on the right. These are actual strings.
So the purples are the strings.
The purple are also strings. The purple are strings which are attached to pancakes in the stack on the same side of the interface. So every arrow is a string. That's the beauty of it. So what happens when you squeeze all yellow lines together? So this wiggly thing means several parallel yellow lines. So we get Nakajima quiver, the yellow one, in this way. So the ultimate boundary condition that you get by squeezing them all is extra variety cotangent bundle to partial flag variety. And W, so that's your Z, is trace of X, that's the coordinate on the base here, the GLN matrix, times the moment map, the famous moment map from T star FL. So just to remind you, the cotangent bundle to flags is a pair flag and nilpotent matrix that respects the flag. So the matrix will look like this. And so you take the trace of this matrix with X. That's the W.
So to get the T star flag, you took a particular sequence of rank, like N
Yes,
minus
yes,
one.
yes. So you know how many pancakes between the yellow
And all
lines?
it's hidden in your wiggly picture.
Yes. So I compressed it. So ultimately, no wonder, because you were doing Nakajima here. Yes, yes, it's a partial. Generally speaking, it's a partial flag. Sorry? The flag variety. Partial flag variety. The dimensions are determined by the jumps in the number of pancakes on the sides of each interface. And the matrix must be nilpotent. And so what is the corresponding Lagrangian subvariety here? As you may guess, the momentum, the Y matrix, by the rules, is the derivative of W with respect to X. So the Y matrix, your movement on the Y cigar, is this nilpotent matrix mu. So here you got your famous Lagrangian, singular Lagrangian subvariety. But in fact, it has more. There's some things growing over it. There may be some fibers. So the actual object here is not just Lagrangian subvariety, but a fibration, fibers living elsewhere, not in your symplectic variety.
So you're taking the Z to T star FL.
Yes, so this is Z, this is W.
Where does your Z come from?
It came from the Nakajima. So here you had yellow lines,
Yes.
and they produced a yellow Nakajima quiver, which corresponds to T star partial flag variety. So one of the examples of Nakajima varieties is T star flags. So this is how it emerged here.
So yeah, as a particular instance of an elaboration on the picture on the top.
Yes. So what would happen if you wanted to place some NS5s here on the wrong cigar? So physicists, I think, call them NS5 prime branes. So remember that we placed all of them on the X cigar. That's why Y is equal to 0. You see, the Y matrix is equal to this Y matrix. That's why I called it Y, because Y is derivative of W with respect to X. And Y is nilpotent, so all the eigenvalues are 0.
Sorry, we say it's very time about Tn, the top nine.
Yes, yes.
What is them?
So matrices X and Y here, X is GLN and Y is the cotangent matrix. Describe the position of pancakes as points in the Taub knot, the eigenvalues.
And the tip of concrete.
So far, I'm describing this side, and this on this side, they're all wrapped on the X cigar. They sit on the X cigar. So how do you see that Y is equal to 0? The braid NS5s. I assume the classical, yes, on the X cigar.
Yeah, that's right.
So Y for them should be 0. How do you see it? The Y matrix here is the derivative of W with respect to X. So Y matrix equals mu, but mu is nilpotent. So that's why they all sit on the X cigar in this language. So what would be the, and this is your famous Lagrangian subvariety, except that the actual object has some fibration. So it's a pretty, if you describe it set theoretically, this object, it's pretty singular. But in this description, it's very smooth. It fits what you need in algebraic geometry calculations. It's a very smooth way, and you can compute. So what do you do with NS5 prime? What if you just want to wrap some of those NS5s on the wrong cigar? The answer is you have to switch X and Y in your commuting variety here. Putting it on the wrong cigar means you interchange X and Y. So from the pink symplectic point of view, from the point of view that we're pursuing, the 3D theory, you have to apply the Legendre transform to this interface on both sides. So if you have a Lagrangian subvariety described by W, there is a way to flip it, changing X and Y. So you'll get an extra variable and a new W. It's called Legendre transform. So this is what you do. You have to add 2 more loops, yellow ones. So these are extra. And instead of the first piece, for example, in the trace, instead of this one, you get 2 pieces now. So it's XY minus W of Y. Yes.
What we want to do that, we had a very nice theory, a story of cooking.
Yes, but now I want to describe a braid line whose M5 is wrapped on the wrong cigar to go to superalgebra setup. Remember that generally we have 2 types of representations, CMN and CNM. So what if I use a different one?
What is the particular reason for this W? Is it, can we choose another W with X squared?
It comes from physics. It's written in stone. It's set in stone.
What if it will be X squared? Physics.
It will be a different object.
But it's meant to be.
Yes.
So what is the true philosophical reason?
At the beginning, physics tells Witten-Waffe and other people tell us the setup that will lead to Chern-Simons and its categorification. So our duty is to follow the setup and do the calculation.
So this shows a W is Chern-Simons.
To categorification of Chern-Simons, yes. Of your and Volodya's polynomial.
Does it mean that W, I mean, Chern-Simons, classical Chern-Simons is somehow that's something to do with
Коля, we're very far from there. Товарищ, мы едем далеко. Sorry for Russian quote. Again, I'll be very happy to tell you how far, but we're pretty. The actual Chern-Simons happens through a set of duality transfer. You do not see it here at all.
So basically, we can prove that there are some secret reasons why this particular type.
Yes. So
We don't know.
so there is a reason.
There only is one.
So you do Legendre, And what is the net result?
Does it have anything to do with structure, something related? Peter is saying something about some intersection.
Let's put okay, so what is the result, the net result of doing Legendre on some of the edges in this quiver? So instead of these two arrows at some place, I put two arrows with the loops and replace W by the Legendre transform. So I'll just tell you what will be the net result for the wiggly line.
So far you just choose a new variable, y2 to something.
So I put two loops, so two extra square matrices, and change the W's. And this is what the result will be. Instead of having here nilpotent matrix, I will have here a general matrix that respects the flag. But in some boxes, it should be 0. That's where the brane is placed on the proper cigar. And in other boxes, instead of 0, you could have anything. So it will be of Borel type. So it will be of a mixed nilpotent Borel type. Sorry? We're not there yet. So slottable will come from D4 in a moment. So I'm just talking about the braid side. So the braid side, if you want to introduce both representations and their shifts, then instead of getting a flag variety as the total boundary condition, you will get the, instead of getting cotangent bundle, where you have to put nilpotent matrices, you will get a mixed matrices, some with zeros and some boxes with anything. Now, what is a D4 prime interface? Now, here we have and I begin with the wrong D4. So this is D4 that is wrapped on the NS5 cigar, so to say, on the proper NS5 cigar. Then it will be this. It's a familiar tooth from a handsaw. If you know handsaw quiver representation for Slotaway. Again, everything here is a string. Since this is a D string, you have strings coming from pink and ending on black. So these are these two, and these are strings from pink to pink. Again, the question goes to string theorists. In terms of Nakajima Cherkis, I would call it a bow edge.
So the box is like a D?
This box represents a single D4 brane. An open string may end on this D4 and on D2, which is pink. And this would create these arrows.
Okay.
So this is the wrong one. So to get the right one, you add the Legendre transform, which means you add two more arrows, two more small circles, two more loops. And so you get the picture that you will see in Nakajima's papers and other people who discovered this, Rybnikov and Finkelberg and Rybnikov. And but of course, without the commuting varieties sitting here. So finally, coming back to this, if you finish this calculation, you will get the Nakajima quiver variety, which is of this type, except it is presented as a joint Hamiltonian reduction of cotangent bundle to flags, and what's called the equivariant Slotaway variety coming from the black side, the result of this handsaw quiver. So this is something very well known. So you get coherent sheaves here because matrix factorizations in that case, yes. So you had boundary and interfaces, meaning inside. And so so I decided to cut through. So this is, so in your case, in your theory, to a two-dimensional surface, you associate a vector space. And if you cut a two-dimensional surface by a line, to a line, you associate a category. So this is so the surface is an infinite strip. And you decided to cut it by dashed red line. So to dashed red line, you have to associate a category. And the answer is the category is the coherent sheaves over Nakajima quiver variety that emerges through these symplectic type calculations with yellow and black interfaces, because they reproduce Nakajima quiver. So in Nakajima's story, supplemented by Cherkis, so the way I would tell it, sorry, just a moment. So in Nakajima theory, you have, in Nakajima Cherkis theory, you have two types of edges, the arrow edge and the bow edge. So both correspond to symplectic varieties. In this case, it is T star home C and 1, C and 2. And the bow variety is this thing. One way, there are different ways to describe it. With some extra condition. So the idea is that you have two types of edges. To each edge, you associate a symplectic variety with the action of GLN1, GLN2. And then, yes, exactly. So if you supplement Nakajima's edge with the bow interface, then you do not need framing. Framing can be presented as bow. Again, I can.
Can these bow edges meet the vertex with the usual edges?
So yes, you can put them in arbitrary. You can put them in arbitrary order, say arrow, bow, and so on. And there is even a rule of moving them through each other, which is called Hanani-Witten move. So there is a story there. So what we learn from this, from the superalgebra perspective, is that there are also arrow prime and bow prime that require X. The Legendre transforms from the point of view of hidden pink symplectic structure. And if you allow these two new types of edges, then you reproduce the varieties for superalgebra. So standard Nakajima for GLN looks like this. Where is it? Oops. Disappeared somehow. Here. And so if you use A prime, B prime, so you allow Legendre transforms, but not from Nakajima symplectic perspective, but from the hidden commuting variety perspective, then you get quiver-like varieties for superalgebras. Same as this one. This one corresponds to a particular, so this variety corresponds to a particular tensor product of fundamental representations, exterior powers, in a particular weight corresponding to how pancakes end on black ones. But if you flip some black ones and flip the cigar, use the wrong cigar, then you get a weight space for a representation of a superalgebra, where you can have both types of representations and superalgebra on this side. but some people will say that they already know it. So let me say now something extra, if people are still alive. So I put you in the condition where I can now say extra without resistance. So the extra,
the opposite in the least super algebra case, you get a category of B brane on the space on.
yes, of that generalized. Well, no, it's still a nice variety. It's still
It's nice, but a category is not super coherent sheaf.
coherent sheaf because the variety is nice. So matrix factorizations reduce. Sorry. Yes, matrix factorizations reduce to coherent sheaves. If your superpotential has a nice critical locus, which means that in transverse directions it is quadratic, then modulo some delicate points that Konstantin Telemann would know, you get coherent sheaves over critical locus. So this is what happens
But
here.
in general, it's not quadratic critical locus. Your superpotential should be like quartic.
So here is an example when you need care. That's this category.
What's the answer for GL1/1? Like the simplest, let's braid. I don't know.
I didn't, to my shame,
He was curious to do that.
I didn't compute. I'll tell you what we did compute with Richard Rozansky. I'm sorry. I hope to give it as a project to my graduate student. So it's the braiding is okay. Well, I didn't compute what happens for GL11 on this side. So let me go into dubious.
All of this builds up to which question should we be asking to categorify GL1/1? Do you actually know how to do it? Can you get
Yes.
something whose other characteristic is a GL1/1 link invariant?
There.
Homological invariant.
So I can give you a braid group action, provided I do some calculations that I'm a little bit afraid of. On the chief scare me, but this is a straightforward calculation. If you want, the problem is with cups and yes, it's well, at least when you have two, when you have two strands, it's easy. So there's some simple examples, and I hope.
But when you say braid fashion straightforward, if I give you an object, do you know to tell me where does the braiding send that object?
I will recognize that your pictures with chart, how do you call them, chart screening charges is much better, I think, for calculation. So but at least you know what to calculate. So
so what I was hoping is like a categorical matrix factorization principle is you did in your work with Lana, something that's kind of confusing.
Let me show you, by the way.
These things into something that actually.
Yes, it is. It is almost as complete. This approach has even some of advantages. It has some advantages as opposed to. So for example.
Like if I give you any object, you actually know how to compute anything whatsoever. Because the first thing you need to do is you need to understand. I don't.
Well. For example, if you do GL2 on two strands, so your variety is T star of P1, and you want to compute an unknot, things like that. Now, this thing gives you more, since. Okay, let me go into dubious. Okay, so this is as I said, something that many of you will say you already knew in simple terms. First of all, this is more than what we did with Kavanagh, because you have two holes on the cylinder, so you have affine moves. So in fact, your categorifying here links. Okay, which, you know what, let me first tell you Countess Kamnitz.
Actually, let me ask you just one thing about your work with Rimani. Did you show there the actual mirror symmetry, 3D mirror symmetry on those quivers?
Okay, let me go there. I don't think that, I'm not sure about mirror symmetry, but Okay, let me
Maybe it's not.
say
Oh, you want to tell about comment?
so before I go there, so what is the actual category that controls braiding in all these models? So you see braiding happens between yellow strands. It doesn't care about slot away side. So this category again can be written as home between flags, cotangent bundle to flags, and cotangent bundle to flags. So this is the category. So if you write it out as matrix factorizations properly, then it's not hard to show that what you get is coherent, equivariant coherent sheaves on derived Steinberg variety. So Steinberg variety means nilpotent matrix and two flags. So the matrices are equal because they are moments that are equated in the middle area. But derived is the feature of matrix factorizations. It's the Koszul duality. So you really get matrix factorizations that do not turn into coherent sheaves. But if you do a proper Koszul duality, then you will get coherent sheaves over derived Steinberg variety. So the word derived appears in a straightforward manner in this approach. Bezrukavnikov and Drish constructed the homomorphism from affine braids into this category, which is monoidal. And I guess Bezrukavnikov and they figured that they needed derived Steinberg. By the way, they also did the version when all the lines are on the wrong cigar. That's the Grothendieck-Steinberg type of thing, but they didn't comment on its relation to superalgebras. So essentially, they did it for even representations and for odd representations. And both are equivalent, as it turns out, which is no wonder, because if you don't have these, then what's the difference between X cigar and Y cigar? If these will distinguish, same or different, but if they all sit on X cigar or they all sit on Y cigar, the answer will be the same, because who cares? Both cigars are on equal footing. So they proved it in a hard way that both of their categorifications of affine Hecke are equivalent. But an easy way is to see that this is the Legendre transform with an obvious symmetry. Okay, so now let me tell you about Kaujus-Kamnitzer as an application. So since you suggested the cylinder, let us do Witten's thing. So let's say here we have coordinate z, an exponential, and here we have coordinate w. And instead of setting w equal to 0, which would give us the 0 section, let us set z equals w to the n and put a single M5. So instead of putting n M5s on the 0 section, we put a single one, but in this shape. So then, if you do the U1 reduction, just follow Witten, and you get you get your D4s, you get n D4s, ending on a single NS5 prime. So this is a standard fact. And here you have your NS5s. So this is the transverse braid direction. And here you have your NS5s related to the braid. So now your pink ones extend this way. So you have a new boundary. Instead of having n black lines individual, you have them held together by NS5 prime.
Where does the NS5 prime come from?
It comes from the following. It comes from taking a quotient by the U1 rotation. This is what happens to this curve. The curve becomes n D4 branes on R cylinder but ending on a single NS5 in the C, in the cotangent space here. Because the simple argument is that for any value of, or any fixed value of W, any fixed value of Z, which is the cylindrical coordinate, you have n solutions. So it projects to a stack of n things. But for any value of W, you have one Z. So they project into one. Anyway, I can refer you.
You can show explicitly that computing the corresponding variant of the quiver variety that exactly that.
Yes, and I'm about to show you very quickly. So now the difference, so you have the same NS5 side quiver. So this remains the same, but so people will tell you what happens when pink lines end on a stack of D4s held together by NS5 prime. You have a single tooth, but it carries dimension n instead of 1. So it's a relatively simple linear algebra calculation that this quiver with the proper stability condition gives you Kautes-Kamnitz from the nose.
Can you go on? But
Yes.
that locus that you're putting here, that breaks some.
Oh, you mean Z equals W to the N?
Yeah, it breaks. Okay. Okay. In their realization categorization, because the space isn't homomorphic symplectic, it's not obvious that you have stereoduality. For example, things that are
Say again?
that
Yes, it's not holomorphic symplectic because this thing.
so it's not called, yeah,
It's-
it's not obvious that you have stereoduality. In particular, it's not obvious that you recover, that you have at all, homological or not. Mirror symmetry are not invariant. The fact that if you take a knot and you change it with its mirror, that's the same as Q to Q inverse. If you space homomorphic symplectic, it's clear that this has to be true. But if it isn't, it's not at all clear. It's not kind of magic. And I wonder if the magic is actually true.
Let us so of course from this picture you see that their variety is not symplectic because or doesn't have to be, because this is n rather than 1. So it's not the Sloterdijk slice. It's a generalization of the Sloterdijk slice. So generally you can have a Hensel quiver with ones replaced by arbitrary numbers. So this happens when you have this kind of placement of a, say, single M5 brane with more general type of polynomials. So they will end on NS5 primes. Now this looks very much, so what you get is, one may call it flag vortex moduli spaces. If I put here several stacks like this ending on NS5 primes, this would result in vortex moduli spaces. But if you put unattached NS5s, then this gives you a flag version because you attach this to the vortex part. Sorry, not symplectic. So Kautes-Kamnitz are not symplectic. It's a funny bundle of let's say P1s. in their original SU2 paper. Neither. It's a convolution of Heike correspondences. So what is this? It seems like M5s are peeling off. So I wonder what is the structure on M3 that allows M5s to peel off the zero section of T star M3. So there are many interesting questions and what this means in terms of Rishtik and Turaev. So it seems that M3 has to be endowed with some extra structure that would allow this peeling off, because generally in Chern-Simons you do not have interfaces. But in your case,
Well, Ben for Webster proven that all these categories are sometimes the same, but it's not obvious.
Kautis chemistry is separate. So it describes.
Well, it's true that categorization of all A and 5 are the same.
Mina, the point is,
It's not obvious.
I would say that, you see, a link is a local thing. You can place a link in a free ball, and all free manifolds are locally the same. And so in this sense, there may be very different physical situations that give you the same knot homology, because the knot is packed in a free ball and doesn't know what happens outside. So if you build a knot out of cups, caps, and braids, it's a very local thing. But what if you, for example, in their calculation, you can take a braid and take a home with another braid. In other words, close the braid circularly in time. They don't do it. They use cups and caps to keep everything local, so to say. But if they close it along a periodic time, this would correspond to some other physics. It won't be in S3, for example. So it will be in this cylinder across a circle with M5s peeling off. Okay, I think so. This also suggests the way to at least see the emergence of matrix factorizations that we use with Kavanov by a similar trick, but this is weird. So if in Taub-Nut, instead of wrapping, so in Taub-Nut, instead of having n M5s being wrapped on the X cigar.
Sorry, so in the previous setting, you could have, of course, considered links that wrap around any and one should.
Yes, and this, so in your case, in Rina-Anno, you get categorification of Rishtik and Turaev in S2 with 2 holes times S1.
Right.
But you're saying that that somehow here, if you did the same thing, it's not obvious you're going to get the same invariant.
You know, in terms of invariance of links, of local links. So if you,
No, I mean, sure that the invariant of a local link that can be shrunk into a ball is different from one that wraps around the circle.
yeah, so if you wrap around the circle, you get something new. And they recognized it. They didn't calculate that part. So if you do the same trick of y equals x to the n on the Taub-Nut side, then you will end up with matrix factorizations that we used with Kavanov originally. So now suppose we do what, now we take your picture with cylinder and zero section, but we use this x equals y to the n on the Taub-Nut side. Then we get something weird if we try to compactify there. But the category now will be the category of matrix factorizations that we use with Misha.
Oh, really?
Yes, and that I can show you as well.
But and now you're starting to break centers that you do need.
Yes, and you see the superpotential in matrix factorizations that we used carries Q weight, but nevertheless homology has that grading. So we can do, so I think this is the first step towards understanding the matrix factorizations there. A separate story is what we were doing with Alexei initially and how we got Hilbert scheme of points, but that was done on the Waffa side of resolved conifold. Similar pictures emerge there as well. But maybe I should stop here and answer it individually. Say it again?
What is it?
It is Mina in the case of GL2. So standard Mina cylinder cross braid time, and what you see, sorry. So what you see here is coherent sheaves over Nakajima quiver variety. That's what Rina used. Exactly in this formulation as an intersection of you see, she was inspired by the idea to use Bezrukavnikov-Risch in order to define action on coherent sheaves over Nakajima varieties. And she essentially did this without saying words about symplectic algebraic geometry. So the Bezrukavnikov-Risch happens here. This is the Bezrukavnikov-Risch coherent sheaves on Steinberg. And this is the Nakajima quiver. So she separated it indeed into Sladoway and flags. And she constructed the action from here to here by these pins. So if she took home between something and something on the other side, she would get an invariant of a braid or tangle inside a sphere with two holes, a cylinder across a circle. So that's what she categorified. And moreover, her affine moves correspond to going around the holes in Mina's cylinder. So that's why she had a fine action. Let me tell you now regarding what we did with R.Rimanyi. So we cheated a little bit, but a little bit. So these Nakajima quiver varieties in this story appear, the same Nakajima quiver varieties appear with R matrices which depend on parameter. What's the name of that parameter? I forgot. Dynamical. No, your very, very old famous, yes, on spectral parameter. So what happens here is that there is a coexistence of two stories in the same realization. There is a coexistence of two stories. So Mina's picture is this. Let me draw a SU2 picture. So she has this red line, which just a moment. Let me think how to say it. Well, let me begin with a simple statement that the Mina's cylinder corresponds to a weight space in the tensor product of fundamentals. Now let us reverse this interpretation. Take the skew dual, the House skew dual. In other words, we'll switch highest weight and weight and transpose. So if you have n fundamentals, say for SU2, this is the same as 2 fundamentals for SUN. In other words, you reinterpret who is the highest weight and who is the fundamental. So in other words, there is another action, which is for us from the Chern-Simons perspective, is the wild group action. And this wild group action, and I think I can explain what it means pictorially in terms of Chern-Simons. This wild group action corresponds to this R matrix with spectral parameter. Yes, if you introduce the let me suppose.
Our spectral parameter can be used in calculation.
Yes, so I'll show you, I think. So suppose you're dealing with SU2. The red line is a funny representation that comes, I think, originated in Witten's paper, which followed his Chern-Simons paper. So Witten wanted to understand how quantum groups appear in Chern-Simons. Mina would say that this is a Verma module. I have some, but
Oh, you mean the representation?
yes.
Here? No, this is exactly what all representation here that enters here is from notation. There's nothing else.
So it's a Verma.
Yeah, I mean, it's a Verma, exactly.
Verma is continuous parameter.
Yes, Verma represents Verma. The thing is put on the face.
Okay, let's
Let's spell Verma.
and these are two-dimensional representations. So if you want to create a basis in this space, so there are several ways to describe a basis in the space of a sphere pierced by all these lines. So they end up on a sphere. That's Mina's cylinder. So the red ones create the hole, and the rest is familiar. So
Incredible.
No,
it's a wonderful. It's for me it was a big breakthrough, at least psychologically. That you can really that you really have to do algebraic geometry with 3D topology in a very literal sense. Somehow I always kept them mentally separate, but now it's much better. So we can create, for example, we can create a basis of envelopes with this Chern-Simons picture. First put all, sorry, just a moment. All the lines that come off. It's the Kaufman-like notation. So if here you have some alpha, here you'll have alpha -1. So I'll draw like this. And then put some lines that come in. And then put a positive braid here. Or negative, let's say positive braid. A short positive braid, which permutes them. And so up to some normalization issues, this will create the one set of stable envelopes. So this will result in coherent sheaves over the Nakajima variety used by, for example, Arena and Hearing in Mina, and that will be one set of stable envelopes. But if you decide to switch these and these, so first they will go in and then they will go out the other way. Then it will. So I'm saying that on T star P1, you have this. Yes. It's yes.
And you choose all going from alpha to alpha minus.
Yes.
Going from alpha to alpha plus.
Yes. So this would be the basis of envelopes corresponding to one choice of C star action. But if you do this, But there is some normalization. Again, this part I wish and so I thought and thought and
I've been talking about what?
so this is alpha. Yes, yes, yes. So these would be coherent sheaves whose K theoretically will become. So stable envelopes can be categorified
Yeah, of course.
this way, turned into coherent sheaves. So you begin with, sorry? I mean, you can have their representatives in coherent sheaves. So that Chern will bring them. T star P1 in this case. So this is GL2 with the two fundamentals. This is a little bit misleading because it's self-dual. So if you look at it the other way, you will still see. Sorry? If you make a certain conjecture about what this one is, then the others are application of positive braids, short positive braids. So with Richard, we did this type of calculation for GL11. So since we were lazy and did not compute the GL11 version of the Slodaway, which is a shame, but we knew what it would be on the flag side. So if we wanted GL11, we needed the dual picture. So we had to interpret flag as giving the group and Slodaway is giving the representations. And this corresponds to spectral or matrix in this interpretation. So we took bundles over P1 instead of nilpotent, we took semi-nilpotent and full Borel and did the envelope type calculation and reproduced the GL11 spectral R matrix.
By GL11 R matrix with spectral parameter, you mean the R matrix for GL11 characterized
by this alpha. Yeah, so they have this alpha thing, the highest weight, and it plays the role of the spectral parameter because you come from these to these. So alpha plays a role. If you simply braid the blue ones.
So it's just a representation.
So here is just who lives on the red line. But this appears to be the spectral parameter because this, what does this one do? Now I'm going into Mina's domain. So this is the holonomy around Mina's cylinder hole, which means that if you dualize D4s, it becomes positions of points of whatever brane emerges, D3. And so you can move them back and forth as points, and this corresponds to playing with the holonomy. So this is what I drew here is SL2. So you can get SL2 with spectral parameter as a transition from this to this, up to some normalization.
But this was in a different world, integral lattice model.
But that's the point. So the point is that we get Nakajima variety out of Chern-Simons, but the same Nakajima variety supports the story about, so this means that our matrix with spectral parameter can be interpreted within the Chern-Simons realm. And I think that what it does because they share the same variety. Only you have to reinterpret. So instead of permuting representations, you
I think that's some kind of situation. So you have an army that's acting roughly speaking on the same space. But when you have a spectral wave, it's an extra wave.
Yes, but here again, the specular matrix happens not when you permute the blue ones, but when you permute the order in which they sit in the order in which they sit on the red one. Whether you first put in and then put out, you see here, just a moment. See, here we have more lines. So on the dual side, it's not SL2 anymore. It's as many as you have, but you have only two representations, this and this. And so when you decide to flip them, that's when.
Maybe we need a little refreshment over there. So, so we can take a break now and continue over there.
Thank you very much for listening.